Let's try to understand FM in terms of harmonics and the sideband frequencies that are generated. Remember from that picture that we get, if we have a carrier and we modulate it, then we generate sidebands that are plus and minus multiples of that modulation frequency. So we can express that with this very simple formula. The generated frequencies are the carrier plus and minus small integer times the modulation frequency. The simplest case is carrier equals the modulator, and so that gives us the carrier and twice the carrier, 3 times the carrier, and so on the plus side. But what about negative frequencies? Well, let's look at this diagram. Here's the carrier at a fairly low frequency, and we're modulating by the carrier frequency. So carrier minus the modulator is 0. Minus twice the modulator is actually minus the carrier. And then we have these upper frequencies as well. The interesting thing about this configuration is that all these frequencies generated are multiples of the carrier, so they're harmonics, which means we're going to hear a periodic signal and get a musical tone, and so that's a very interesting, cool thing. Just 2 oscillators, and we generate lots and lots of partials, lots and lots of harmonics. Okay, and in fact, roughly the bandwidth is 2 times d plus m, where d is the depth of modulation and m is the modulation frequency. But getting back to negative frequencies, suppose we increase the depth of modulation a lot so that we get lots of sidebands. So now we have all these sidebands. Some of them are shown, they're shown at different amplitudes and including negative amplitudes to reflect the fact that they are described by these complex Bessel functions, and in fact, they do have different phases, or positive and negative. And so what does this mean in terms of the signal that we hear? Well, each of these negative frequencies corresponds to a positive frequency. And so I've taken each one of these negative ones and just drawn it next to the corresponding positive frequency. And effectively they add. And sometimes they're in phase and they add constructively. Sometimes they cancel, they add destructively. And so once again, the amplitudes are complex enough to begin with, but now that some are canceling others, we get very interesting evolution of the spectrum. And that is one thing that gives rise to this characteristic FM sound. And another aspect of this is it makes it very difficult to actually predict exactly how the spectrum is going to evolve. Or not so hard to, it can be calculated from these formulas using Bessel functions, but if there's a particular spectral evolution that you're looking for, it's very difficult to go back, next to impossible in general, to invert these computations and figure out what all the coefficients should be. So let's look at a classic FM synthesis sound for doing something that's characteristic of a brass instrument. So brass instruments have a rapid rise in the upper partials as the sound gets louder. So in particular, at the very beginning of the sound, you go from no sound or very quiet sound to full volume sound, and that involves introducing higher partials. And we can increase the energy in the upper harmonics or upper partials by increasing the depth of modulation with FM. And so that's what we do. We use a 1-to-1 carrier to modulation frequency so that we generate harmonics, and we rapidly increase the depth of modulation. Again, let me remind you, when I say depth of modulation, that means how many hertz is the carrier increased by and decreased by through the frequency modulation. So let's go back to our code and find our FM brass sound. It's just one line of code here. And so here we have the frequency will be C5, and the modulator will also be C5. And we're just multiplying the modulator by this piecewise linear envelope that's going to go from 0 to 2000 in 50 milliseconds. That's kind of a characteristic brass attack time. And then at time 1, it's going to reduce down to 1000. Let's play it. Play it again. All right, so that's not exactly a trumpet sound, especially to me as a trumpet player, but there is something characteristically brassy about that sound. What about odd harmonics? We can easily create odd harmonics by setting M equal to 2C. So this, the modulation frequency is double the carrier frequency. That's one fast vibrato, but the result is that we get C itself, C plus M, which is 3C, C plus 2M, which is 5C. So these are odd harmonics. We also get negative frequencies, but fortunately those come out to minus C, minus 3C, minus 5C. So they're also odd. Now, why would we be interested in odd harmonics? Well, let's try it. Here is an example we've created where the carrier frequency is C4, the modulating frequency is C5, which is an octave higher. It's exactly double the frequency. So we have this 2-to-1 ratio, and we are going to increase the modulation from 0 to 4000 hertz. That's the depth of modulation over the total duration, which is 10 seconds. And you should hear something maybe characteristic of a clarinet sound. Okay, so we can have other schemes for harmonics. If we let M equal I over J times C for small integers I and J, and let's let F equal C over J, then M is equal to I times F, C is equal to J times F, so C plus M is I plus J times F, C plus 2M is 2I plus JF, etc. So that essentially means that all the frequencies we generate are multiples of F, where F is C over J. I and J are, again, are small integers. So any combination of small integers will give us harmonics of some fundamental frequency. So let's look at an example of that. Here we have a ratio of 5 to 3. How did we do that? Well, we actually constructed, we took 3/5 times step to hertz of C4 as and converted that back into a step called mod step. And so now the carrier is C4, the modulator frequency is mod step, and we will increase the depth of modulation from 0 to 4000 over 10 seconds. Okay, so according to our formula, the fundamental should be, given this 3 to 5 ratio, fundamental should be the carrier frequency divided by 5, and so we've calculated that as fundamental step, and we'll just use pluck to synthesize that fundamental frequency. it's a low pitch, but it seems like it's the same pitch. I mean, the FM it's a very different spectrum, but we've got the same pitch there. Another thing we can do is look at carrier to modulation ratios that are not simple integer ratios. Then the resulting frequencies are not harmonics. The negative frequencies are not harmonics. You add them together and they're not harmonics. It's something that does not have a characteristic pitch, and we can easily make some examples. Here's C4 as the fundamental, or the carrier, and D4 as the modulator. That's D4 is about 6% higher in frequency. No clear integer ratio there. So what was the pitch of that? I don't know. There are a lot of kind of pitches combined inside there. Here's another example. So it seemed to start out having a pitch, but that was just the carrier, C4. Once we started introducing all of these sidebands at non-harmonic ratios, the signal got very complex. And I'd like to point out that, you know, when you do FM, you're not restricted to 2 oscillators. You can make 2 FM sounds and add them together. You can do even more complex things of modulating an oscillator with a complex FM sound. Lots of combinations, but putting things together is relatively easy to do. It doesn't take a lot of computation because we're talking about small numbers of oscillators. And so here's an example just with 2 calls to FM OSC, and we'll listen to it. So a much richer, much more complex sound because there are just a lot more partials involved and different modulation rates and so on. Now, another thing we can do with FM is create the effect of filters or resonances, sometimes called formants. Formants are very significant in the human voice. This is how we make vowel sounds, by changing the shape of our mouth, which is, and other things to create filters, basically, that process our the sound that we make with our vocal folds. We'll learn a lot more about this later. The point now is that FM can simulate resonances by placing a carrier near the desired resonant frequency and then modulating it to create nearby harmonics. So imagine if we had a harmonic spectrum that started way down here at the low end of frequency, and but we filtered it with a resonant filter that emphasized frequencies in this region. Okay, the result would be a set of harmonics, equally spaced sinusoids in this frequency region, and that's exactly what we get when we modulate a carrier with. Actually, here the modulation frequency would be the fundamental frequency because that's determining the spacing of the harmonics. Anyway, let's go over back and look at one of these simple setups. So here we have frequency of C5 being modulated by C3. So we should hear the fundamental frequency will be something like C3, and it will apparently have a resonance around C5. So I don't know what that sounds like to you. It's actually, from one perspective, it's a very electronic kind of sound, but if you think about it, you can perceive that as having a little bit of a vocal quality because this resonance is sort of tricking our our ears and our perception into thinking that some filter was involved, and maybe it's a voice. I'm gonna jump through some code and just give you another example. Let's play this. So I don't know if that sounds at all like an ah sound, but that was a couple of simulated resonances calculated to approximate the resonances that humans use for making ah, and that was done with FM synthesis. I'm going to leave the details of the code to you to read on your own. So, in summary, FM synthesis is powerful because it produces time-varying spectra at very low cost. The simple case is we have only 2 oscillators, and also with simple parametric control. We did all of these examples with just a few simple envelopes, changing the depth of modulation, and that gives us very interesting space of sounds that are very musically useful. We can control these sounds by changing the carrier to modulator ratio, which determines sort of the structure of the harmonics, even harmonics, odd harmonics, all harmonics, inharmonics, and so on. And we can even create simulation of formants or filtering effects. And finally, just remember that the depth of modulation determines the number of partials. Obviously, if the depth of modulation is 0, there's no modulation, then there's only going to be one carrier frequency, one sinusoid. But as you start wiggling that in frequency and increasing the amplitude of the modulation, then you generate more and more partials.